CPU and RAM behave fundamentally different, and it is so easy to misconfigure them when setting resource limit and request for your applications. This video is specifically for CPU, but in order for us to understand how the CPU works, let's understand how memory also works, because when we understand the model behind how the memory works and how it's been allocated, we can better appreciate how the CPU works. I'm not going to talk about the mechanics or the deep dive into how the Linux kernel actually enforce this. I'm just going to be talking about how they works in terms of request and limits. So with memory, when you request a memory or set a limit for a memory, what happens is that the Linux kernel reserve a certain portion of the memory for that process. So that process is bind to that allocation. In other words, memory is incompressible, right? Once you bind it to a particular process, it is stuck with that process unless that process is killed. But with CPU, that model doesn't work with CPU. You see, CPU is compressible. It means that you can have a lot of process using one CPU and no one is actually hogging that CPU to itself. Now, this is what I mean. With memory, a particular allocation or a particular portion of memory is reserved exclusively for a process. But with CPU, processes takes their turns, right? It is called time slicing, whereby one process runs for some time and then give way for another process. And all of these are being enforced and managed by the Linux kernel. This is the tricky part, and this is where most people get confused. When you set a resource limit and request, there are two things involved here. We have the request and the limit. The request is fundamentally used for making decision on the placement of the pod. So this is what the scheduler sees when making an informed decision on where to place your pod. It has nothing to do with how much resources the pod or the container or the process is actually using at that point in time. However, the limit sets the maximum amount of resources that a pod or a process is allowed to consume. Anything more than that is going to lead to a penalty. So with memory, when a process tries to use more than what is allocated to it, the Linux kernel terminates that process. It kills it, which is the popular OOM killed error that we often see in Kubernetes. But with CPU, it is different. Nothing happens to the pod keeps running. But under the hood, the pod is being throttled. And you might not even see this. The only way for you to see that your pod is actually being throttled is when maybe users are experiencing latency trying to access your application or trying to connect to your API. Let's take a very practical example.